Initial dominant infection site is the nasopharynx, which if you look at these visuals is marked in red. It is the region where the two sides of the airway converge and it forms the upper part of the pharynx. So going back to the first question, what are the hazardous droplet sizes? We can try to figure out the droplets that would land directly at this initial dominant infection site, that is the nasopharynx, during inhalation. To answer that, I've simulated a wide range of breathing conditions by replicating flow rates from 15 to 85 liters per minute, and they stand in for moderate steady breathing to forceful inhalation. Against the ambient airflow, I have tracked droplets sized between 0.1 to 30 microns. I did not go any bigger because beyond this size scale, the droplets, the respiratory droplets, after being expelled by the infected individual, would undergo prompt gravitational sedimentation. So within this size range, I see that the nasopharyngeal deposition peaks for the range 2.5 to 19 microns. For these simulations, the density of the droplets was 1.3 gram per ml, which is typical of respiratory ejecta that has undergone environmental dehydration after being expelled. But let's imagine that we are in a humid climate. The environmental dehydration is low, and the droplets, they retain their watery components, and as such, the density is close to that of the oral fluids, which is mostly watery in nature. So with 1 gram per ml as density, the size range that lands directly at the nasopharynx is revised just slightly to 3 to 20 microns. Let's now do a quick check of these sizes using a simple scaling analysis using Stokes number. Given all the flow and morphological parameters staying the same, and also based on the droplets landing at the same eventual spot, which in this case is the nasopharynx, we can show that the ratio of the material density of the droplets should be inverse squared ratio of their sizes. So over here, I'm talking about two different densities, 1.3 and 1 gram per ml. If we plug in the minimum diameter and the maximum diameter for the heavier droplets, the corresponding numbers for the lighter droplets come out to be 2.9 and 21.7 micron, which is quite close to the CFD based prediction. So this is the hazardous size range, which answers the first question. Let's now go into the second question. What is the infectious dose? Again, this is the minimum number of virions that can start the infection. To answer this question, we need to figure out how many virus particles would be there in a droplet that has just been expelled. And for that, I looked at the papers that are being published. So this study is from PNAS last year. They report that the probability that a 10 micron undehydrated droplet would carry at least one virion is just 0.37%. I have developed a simple mathematical model to check these numbers, and then I'm going to link that model with the CFD predictions on the droplets that we need to be worried about. So for the model, I need some virologic data. So this group in Germany, they have assessed the viral load in hospitalized COVID patients. These numbers, by the way, are all for the alpha strain from last year. They found that the average viral load is 7 times 10 to the power of 6 virions per ml. So we can quickly figure out how many virions would be there in a droplet of D micron, which is shown as capital N over here. In other words, to come across one virion in these droplets of diameter D micron, we need to check 1 over this capital N number of droplets. Let's call that small n. So the probability that there is at least one virion in a droplet of D micron is P, which is 1 over this small n times 100%. Let's plug in the value for D in this formulation. So plugging in D 10 micron, we do indeed get 0.37%, which matches up with the previous study. So we can now use this number N to figure out the viral load that would be transmitted by the bad droplets to the initial infection site. For that, we also need to know what is the exposure type, or what is the size distribution of the droplets that are coming out from the infected individual. So I looked at this particular paper from 2009, its pitch emission data, let's imagine that the infected individual is emitting this particular size distribution. Then using the CFG predictions from my work, we can figure out which ones and how many of these droplets are going to be landing at the nasopharynx of the infected individual. So using that perspective, we can figure out that if someone is exposed to the infected individual for 5 minutes, and if the infected individual has an average viral load, 11 virions would be landing at the nasopharynx of the exposed subject. But on the other hand, if the infected individual has peak viral load, 3,800 virions are landing over 5 minutes of exposure in the other subject. Based on this, and the fact that 2.5 hour has been reported in a number of super spreading incidents last year, we can figure out the infectious dose, the viral load that can stir the infection. From my calculations, it comes out on the order of hundreds, the precise number being around 300. And this number has since been supported by a few other published studies. It is remarkable how low it is. You can look at the influenza A virus infectious dose. It is almost 2,000 to 3,000. This implies that SARS-CoV-2 is 10 times more contagious than a flu virus. Also, as I said in the beginning, this in silico framework should be applicable to other respiratory pathogens. Since early 2000s, we know that for SARS-1, the infectious dose is somewhere in between 43 and 280 for 10% and 50% adverse symptoms. And it has been conjectured that for SARS-2 as well, the infectious dose should be of the same order, which agrees with our estimate. So this paper has now been published. Feel free to check out for the details that I could not cover in this talk. And this is an ongoing topic. And these are the questions that I jotted down last night. There could be many others. So for example, we need to merge the upper respiratory tract deposition data with the subsequent complex transport of the mucus. We need to connect the airborne transport mechanics with the data for the new viral strains. We need to validate the droplet sizes and the infectious dose. And we also definitely need new data on the ejector size distribution, especially for infected subjects. So related to this topic, I have been working with a few industry-based and academic colleagues, and here are the students who are helping me out. I'd like to leave this as the parting slide. These are some lines from Rajat's paper from last year. Thank you.
The floor is open for questions, and there's a mic back there.